This is the third video of a multi-video tutorial series in which we're using the FluCoMa toolkit to create a two-dimensional sound browser that we can perform sound slices in within a two-dimensional space. In the previous videos, we first used FluidBufOnsetSlice to analyze our buffer, look for spectral onsets, and then tell us where those spectral slice points should occur. Then we used those slice points to analyze the different drum slices in the drum loop, and eventually sort them according to the spectral centroid of each slice and play them back in that sorted order. In this video, we're going to add another analysis to this and then use that second analysis to plot our drum slices in two-dimensional space. So we'll start from this code that we have left off from in the last video. We'll just add some more analyses here in our analysis section. So right now we're doing a spectral shape analysis. We're using FluidBuf spectral shape to get the spectral centroid of the sound slice, which remember is a time series of spectral centroids with however many values as there are FFT frames in the slice being analyzed. And because each of these sound slices might be different lengths and might have different numbers of spectral centroids in the time series that is describing it, we're using FluidBufStats to find the mean or average spectral centroid across that entire sound slice, so that we can describe each one of these sound slices using just a single value. Then we're using FluidBufCompose to organize all of those mean spectral centroids in order in a buffer called mean centroids, that after we're doing all the analysis, we then load mean centroids back to the language so that we can find the sorted ordering and play them back using this little play slice function that we created in a previous video. So in order to add the second analysis to this, we're just going to put it right in here. I'm going to add another analysis. I'm going to delete this BufCompose first, and I'm going to add another analysis right here, and I'm going to put FluidBufLoudness. FluidBufLoudness is going to tell us about the loudness of a sound slice. We'll tell it process blocking, tell it which server this buffer is on. Our source buffer here is again going to be the buffer called SRC. We want it to analyze the buffer that has the drum slices in it. And then for start frame and num frame, we're going to want to analyze the same section of the buffer that we're analyzing with FluidBuf spectral shape. So I can just copy and paste this down here. That'll be our start frame and number of frames to analyze. We again have to give it a features argument here. That'll be a buffer that it should write the loudness features that it discovers into when it is done with the analysis. I'll call that buffer loudness. And then I'm also going to provide a select argument, just like I did in FluidBuf spectral shape, to tell it to return only the spectral centroid. And then again in FluidBufStats to tell it to return only the mean value. Here I'm going to say select should be loudness. And this loudness here is one of the two analyses that FluidBufLoudness is able to return, and returns by default. So if you look at the help file here, we can see that it will return a multi-channel buffer with 2 channels per input channel, one for loudness and one for the true peak. So in this case, I'm only interested in getting back the loudness analysis. I'm not interested in using the true peak analysis, so I'm just passing in the symbol loudness inside of the array to the select object here. Now we're saying that there's a buffer called loudness. We better make that buffer. We're not actually using this mean centroids buffer anymore, so I'll delete that. And I'll also delete here where we bring the information back to the language. And now what I'm going to do is I'm going to also take a statistical analysis of the loudness values. So I'll use FluidBufStats. But instead of telling FluidBufStats to analyze the spec buffer, I now want it to analyze the loudness buffer, the buffer that's going to have the time series of loudness values that describe my sound slice. I'm going to leave this select argument as mean because I want FluidBufStats to return just the mean value. And then here in stats, I could leave this as stats in some cases and use this buffer twice. In order to be really clear right now, I'm actually just going to make another buffer called stats2. And we'll just make sure we're not accidentally overwriting anything in our buffers. So now, for each sound slice, I have a start and an end position in my original buffer called source. I'm calculating the number of samples that I should analyze, so each one of these drum slices that is to be analyzed. And then I'm using buff spectral shape to get spectral centroid analyses, and then finding the average spectral centroid and storing that in a buffer called stats. And then I'm also using FluidBufLoudness to get a loudness analysis of that drum slice, which is again a time series of loudness measures in decibels. And then I'm using BufStats to get the average or mean loudness across that sound slice and storing that into a buffer called stats2. Now what I ultimately want to do here is I want to store all of these sound slices, their mean spectral centroid and their mean loudness, into a data set. So I'm going to make a data set that will eventually store all of this in. And then down here, after we do all of this processing and sync with the server, I'm going to just print that out. And we'll see it in the post window. Now, in order to get these values into my data set, I use a method called addPoint. An addPoint here is going to take a few arguments. The first one is going to be an identifier that we will use to uniquely identify this sound slice, or the values that we're adding to the data set, being the mean centroid and the mean loudness. And so what we're going to use for the identifier here is we're going to use this counter variable I, so that each sound slice will be identified by the integer or the index where it exists in the original buffer source. And then I need to pass addPoint a buffer here, and this buffer needs to contain the data that I want to actually add to the data set. So I'm going to make a buffer in a moment to do that, but for right now I'll put in here point because that's what I'm going to call the buffer. So I'll make this buffer point. And now what I need to do is I need to get the mean centroid that is right now in the buffer called stats, and the mean loudness that is right now in the buffer called stats2. I need to get those values out of those buffers and put them into my buffer called point. The way I can do that is with FluidBufCompose, just like we did before. Tell it which server this is on. First, I'll copy out of the buffer stats. Start frame and num frame I can actually leave blank here because these buffers, both stats and stats2, are only going to have the one value in them, the mean centroid and then the mean loudness in stats2. So I'll just leave that as is. But what I will do is I'll say destination should be point, the buffer that I want to copy these values into. And then also I need to say dest start frame, and I'm going to put a 0 right here. You see the default is 0, so I could leave it blank here, but in a moment I'm going to change that value and make it something else. And so we'll be verbose here and just be really specific about where we're going to be copying that value out of stats. So then I'll say again, FluidBufCompose. The buffer is on the server S. The source is this time going to be stats2 because now I'm going to want to copy that mean loudness out of stats2. Again, I will say the destination should be point. And now I will say the dest start frame should be 1. And what this says is that the value that's going to be copied out of the buffer called stats should end up in the destination buffer at frame 0. And then the buffer that's going to, or the value that's going to be copied out of the buffer called stats2 should end up in the destination buffer in frame 1. So what point will be at this point is a one-channel buffer that has 2 frames, and those frames will contain in index 0 the mean centroid, copied out of here, and in index 1 the mean loudness, copied out of here. So now if we run this, I get an error, load to float array. Yes, I need to do the analysis from the last videos. So here's the sound file that we'll analyze, which you probably have heard before. And then we'll use FluidBufOnsetSlice to do the slicing. We'll look at it, says it has 42 samples. That's 42 slices. That's more than I want. I'm going to raise this up to 0.5 as it was in the other videos. We can see I have 24 drum slice points now. You can look and see where those are. And then I'll redefine this function play slice because we'll be using it a little bit later. And then down here I will do the analysis, which again will use this indices buffer that has the slice points in it and that we've loaded into it right here, and use those slice points as start and end positions of all of our drum slices. So now we can see it's doing all this printing here. I'll actually just delete this. And we can see that I have a data set that has 23 rows, which is good because we're expecting to have 23 drum slices that's made out of 24 slice points. It has 2 columns, and sure enough, we can see that the first column here, or the column index 0, looks like a bunch of spectral centroid values, and the column index 1 here looks like a bunch of loudness measurements in full scale, dBFS. So now we have a data set full of data, with the identifier being the index of the slice as it occurs in the original source buffer. And associated with this identifier is a mean spectral centroid value from that sound slice and a mean loudness measure from that sound slice. So now that we have these 2 dimensions, we can plot it in 2-dimensional space. I'm going to delete this stuff from the last video and go down here and do some plotting. So in order to plot it, the first thing we need to do is we need to load the information from the server, because that's actually where this data is living right now, is in the data set on the server. We need to load it back to the language. So we can do that by saying our dataset analyses.dump. And it will return a dictionary that contains the information in the dataset. You can see here there's a key called data, and then inside of that there's a dictionary which has an identifier associated with the values that make up the data point. Here's another identifier. So this is slice index 1 with a spectral centroid and a loudness, slice index 20 with a spectral centroid and a loudness, etc. So what we can do is we can send this dictionary to an object called FluidPlotter. And this is going to plot for us these sound slices or data points in the 2-dimensional space that exists in this data set. So I'll say dict is dict, and then we'll see what happens. So here we need to defer FluidPlotter to a lower priority thread. And now we see here's our FluidPlotter. Now we don't see any of the sound slices plotted here, and that's because FluidPlotter by default is showing us in the range from 0 to 1 in both axes. And of course our data is in the range of spectral centroids, which is in the many thousands, and loudness, which is all going to be below 0. So what we'll need to do is we need to change the range of the plotter. So in here we can just say xmin, which is our spectral centroid, should be 0. Xmax, which is our spectral centroid, should be, let's just make it 20,000. Number that'll probably be much too high, but we'll be able to see any spectral centroid in that range. And then for ymin, this is loudness, let's make it -100. And for ymax, let's make it 0, because that's dBFS. So now if we plot it, we can see here are our data points. What I want to do next is I want to be able to move my mouse around on this plot and have it tell me which sound slice, which point is closest to my mouse, and then maybe play back that sound slice, right? So what I'm going to do is I'm going to pass into FluidPlotter here an argument mouse move action. And this is a callback function that will get executed every time the mouse is clicked or dragged on FluidPlotter. So the arguments that it passes back are the view, which is going to be itself, the FluidPlotter, followed by the X and the Y position. If we just plot that, we can see X, Y, post. And if I move around here, we can see that it's giving me the position of the mouse in the range that is specified by the range arguments here. So as I move from left to right, I have low spectral centroids up to high spectral centroids. And as I move from bottom to top, I have very low, almost -100 dBFS up to 0 dBFS. So now what I can do is I can take the mouse position and find which point is nearest to it, or which is the nearest neighbor. There's a data structure in FluCoMa that allows us to do this sort of nearest neighbor lookup really efficiently, and that is called a KDTree. And the way a KDTree works is that we'll tell it which data set we want it to fit to, and then we'll analyze that data and create a tree data structure that will allow for really fast and efficient lookup of the nearest neighbors. So we'll say, initiate that KDTree, and then we'll say tree.fit, and the data set we want to fit to is going to be our data set called analyses. So now what we can do is each time the mouse gets moved, we can use this tree to look up the nearest neighbor. In order to tell it where the mouse is, we first need to get our mouse position into a buffer, because in FluCoMa, we're always using buffers to pass information between different objects on the server. So we'll make a buffer called point, just like we did before. And we'll specify the k, which is the number of neighbors we want it to return, should be 1. And then we'll make an action here, which will give us the nearest. Now I made this buffer called, or I said there's a buffer called point, so I need to make one. I'll make it right here. And I'm just going to allocate it with 2 frames because I know that I'm always going to have 2 values that I'll be putting into it, the mouse X and Y position, which of course represents a spectral centroid and loudness. So now that I have this buffer made, right here I can just say point.setN, which will set those values into the buffer. And then right after that, I can say KDTree should use the values in point as the position I want to find the nearest neighbors of. And then once it finds that, it will execute this action function, which will post the nearest to the post window. So if I click right here, we can see that that is slice index 6. And if I click right here, that is slice index 19. If I click right here, that is number 2, etc. So now what we can do is we can actually take this index and use it to play back our sound slice. Remember that the way we created this play slice function is that all we have to do is pass it the index of a sound slice, which is the position that it occurs in the original source buffer. And it's the identifier that we use to uniquely identify the values of that sound slice in the dataset. So here we can just call play slice and tell it the nearest. Now nearest here is actually going to be a symbol that it's going to get, that's getting passed back to the language. So here I'm just going to call as integer. Now we can hear that it's double triggering, and that's because when I click down, it triggers, and when I click up. So the way that I'm going to handle that right now is I'm going to keep track of what was the previous sound slice that it found to be the nearest. And then when I find out what the nearest is, I will say I should only play if nearest does not equal previous. Then we'll play the slice. And if we do that, then we'll say that previous equals nearest. And now it's only playing each slice one time. Okay, and another thing I want to add to this is that I want to highlight which sound slice it's currently identified as the nearest. And I can do that by saying, if the nearest is not previous, then I'll say the view, which again is the FluidPlotter here, dot highlight should be the identifier, which is the nearest. And now if I click, we can see that it makes that dot a little bit bigger so that we can see which one is the nearest. So now I can click and drag around on this. Now you'll notice that as I move across this, when I move left to right, we can see my mouse tracks pretty well left to right where that highlight dot is. But as I move up and down, it's really not tracking where it is. And that's because we have a pretty large mismatch of scale here. So if we're trying to find the distance between 2 points, for example, between a sound slice and our mouse position, and we have a great difference in scales in the 2 dimensions, we're going to run into a problem that we were just seeing. So if we think about the 2 points as being 2 points on a grid of a city, the distance between the two we would find using the Pythagorean theorem, right? We'd find the distance in one dimension between the 2 points and the distance in the other dimension between the 2 points. You can see here I have spectral centroid as being roughly about a range of 10,000 hertz, maybe from 2,000 to 12,000 or something like this. And then the range of loudness being about 100 decibels, maybe from -100 up to 0 dBFS. So the range of the spectral centroids here is about 100 times larger than the range of the decibel values. So if we want to find the distance between the two of these, we'd find the hypotenuse of this triangle. But we notice that because one of the ranges is so much larger than the other one, the length of this orange line, the hypotenuse, or the distance between the two, most entirely depends on the length of this one dimension. This little distance here is really not having that big of an impact on ultimately the distance between these 2 points. Even if we were to double this length or triple it, the length of this orange line, the hypotenuse, is really not going to change that much. Whereas if we were to halve or double the length of this red line, the larger range dimension, the length of this orange line would change quite a lot. So the issue here is that if we're trying to find the distance between 2 points and we have 2 scales that differ greatly in range, such as this, the dimension that has a much larger range is going to have a much greater impact on the distance between points. So one solution to this problem is to use a process called normalization. And what we're going to do is we're going to take the full range of centroids and the full range of loudnesses, find the minimum and the maximum of each of those ranges, and then scale them so that the full range of loudness will be between 0 and 1, and the full range of centroids will be between 0 and 1. So now, because both of these dimensions are being scaled to the same range, 0 to 1, the hypotenuse, or the distance between 2 points when calculated this way, will be equally weighted by each of these dimensions. We can normalize in FluCoMa really easily using the FluidNormalize object. And I'm going to tell FluidNormalize that I want it to perform fit transform on my dataset called analyses. And what this is going to do is it's going to analyze my dataset called analyses, find the minimum and maximum value in each of the 2 dimensions, and then remember those values so that when it does the transform, which in this case it'll do right after the fit, it will scale my values in each dimension appropriately so that now all values will be between 0 and 1. So I'm also going to make a new dataset here called normed, which will be the dataset that will hold the normalized data. So now if I run this and look at normed, we can see that it has the same identifiers as in analysis, but now all of the data is normalized, whereas in analysis it is still in those very different and very large ranges. So now instead of using the analyses dataset to dump and plot, we will use normed. We can see here that all of my data points seem to be up in this very top corner, and that's because I still have these ranges specified in the FluidPlotter here. So I will just get rid of these so that they will default to being between a min of 0 and a max of 1 in each dimension. And now I can see here are my sound slices spread out in this normalized space between 0 and 1. And if I move my mouse around now, we're actually not getting what I think we should be getting because I need to fit my KD tree that we're using here to my new data set called normed. So rather than having the tree fit to analyses, I'm going to fit the tree to normed. And now if we run this, we're getting the KD tree finding the nearest neighbor to the mouse in this normalized space. And we can see that now the mouse position tracks much more appropriately, as we might expect, with the nearest sound slice to its position, because we've normalized each of these ranges so that they are no longer very different in scale. So if we investigate this a little bit, we have the quieter sounds down here, the lower average loudness, and then up here we have the louder sounds, and on the left here we have the sounds with the lower spectral centroid, and on the right here the sounds with the higher spectral centroid, the symbols. So there's a couple things we might do at this point. We might look at some different ways we might want to organize this data in two-dimensional space. So for example, with drum hits, rather than using the average loudness to describe the drum hit, it might actually make more sense to use the maximum loudness of the drum slice to describe the drum hit. And this is because that maximum loudness is actually going to have more impact on how we perceive the loudness of that drum hit. Especially if we have a long slice that has a very loud attack at the beginning, and then as that attack decays, the loudness is low for a very long time. That would bring the average down quite a bit because of all of those loudness analyses that are much lower than the actual drum hit itself. So in order to give us the maximum loudness, we can just tell FluidBufStats that when it does the statistical analysis of the loudness buffer, rather than giving us the mean, we should have it give us the high percentile, which by default is the 100th percentile or the maximum value in the buffer. So now if we rerun the analysis and renormalize the data and refit the KD tree and then plot it, we can see it's organized a little bit differently here. and maybe a little bit more aligned with our perceptions of what we would want to find in this two-dimensional space. Just like we did in the previous video, another thing we could do is we could lower the threshold on our slicer to end up with more slices. So I'll change this threshold to 0.05. Now it looks like we have 42 slice points rather than the 24 that we had initially. We can use those slice points to do the analysis. Here's our 41 different slices named 0 through 40 from the 42 slice points. We will then normalize our data again, fit the tree to that data, and plot it. So we can see we have a lot more slices here. And also, there's a little bit more separation between the quiet sounds down here and the loud sounds up here. The lower spectral centroid kick drum sounds are over here on the left, and these symbols are over here on the right. So again, once we get this plot here, there's some things we can go back and change with the slicer, with the analysis, with the statistical summary of these analyses that might give us a different organization in 2D space in how we might want to approach these sound slices. And at this point, there's a couple things we could do. Is we could navigate this with the mouse like this. We could connect it to a MIDI controller perhaps, or some other type of control interface, and perform the two-dimensional space this way. In the next video, we're going to replace this drum loop with a much larger corpus of sound so that we can have a more diverse set of sounds in our 2D plot to explore and perform with.